Okay, this week we're moving on, getting into moisture. We see moisture in the air all the time. We feel it when it gets very sticky and humid out there, or you see fog sometimes, or clouds in the sky, or precipitation like rain or snow on you. All of that refers to moisture, and it is kind of an important part of meteorology. So let's get into it a little bit here and talk about it, see what we can find out. So, first, how does all this water get in the atmosphere, and how does this relate to keeping the planet habitable like we are? Well, there are things like atmospheric rivers. Here is a classic one. Notice the band of clouds in the Pacific running all the way into the Pacific Northwest, streaming all the way into the South Pacific. That band of clouds literally picked up moisture all along its route there and dumped it when it got up into the Pacific Northwest, a lot of the rain there. So these atmospheric rivers actually occur all the time. You can really spot them on satellite pictures. Here you can see the impact on the Northwest. Water vapor comes in, hits the first range that's close to the coast. Some precipitation falls, but then it hits the higher range. Here you get heavy rain, heavy snow. This fills up the basins and all that. Last winter, there were several atmospheric rivers that impacted the mountains in California, for example. I know for a fact that Yosemite got over 15 feet of snow in one storm. So that was off of an atmospheric river. Other areas like Lake Tahoe do it all the time as well. Sometimes the Pacific Northwest. These things are channeled. They don't cover all the West Coast at one time. Maybe they'll come in the southern part, or maybe they'll come to the northern. We get atmospheric rivers on the East Coast. Sometimes they came up from the Gulf of Mexico and maybe into Ohio even. They dump a lot of rainfall. Some of that atmospheric moisture may have even developed in the Caribbean, for example. So there's not a lot of water vapor in the atmosphere, actually. If you condensed it all out, we might have an inch of rain everywhere in the world, which wouldn't be a whole lot to really add to the amount of water in the lakes or anything. But there's a constant exchange of water between the Earth's surface and the atmosphere. For example, over the ocean, we get lots of evaporation. Oh, yeah, we get some precipitation back as well, and some runoff back from streams and rivers coming into the ocean. But some of that precipitation is transported by the atmosphere. That moisture comes across, hits the mountains. Maybe it snows up there. Some of it goes into the land so we can have plants grow. And some of it comes back from those plants. Literally, plants give off moisture as well. I'll give you a classic example of that one. They did a study down in Oklahoma. Winter wheat crops. I know you have them in Ohio. They have a large area of winter wheat down in Oklahoma as well. When that winter wheat crop begins in the spring, dew points begin to rise in much of Oklahoma, actually rising into the mid to upper 60 dew points, which is just a measure of moisture. They cut that winter wheat usually at the beginning of July. When they cut it, all of a sudden the dew points fall. They go back into the 50s. So literally the moisture was coming up out of the ground into the plants, and the plants were releasing some into the atmosphere. Of course, that also helped to feed some thunderstorms, which probably then transported it back into the ground. So you can see this whole process works together. So how do we get water in? Well, evaporation. We know that evaporation occurs because we see a water puddle disappear, for example, when the sun's heating it. This just means molecules are entering the atmosphere as a vapor and then return as a liquid to the water surface later. Condensation is when they go from a water vapor into a liquid, and they condense. If you have a very cold drink out in the summertime when it's so hot, the moisture is condensing on that glass probably. Transpiration is just what I talked about with plants bringing up. Sublimation is ice or snow becoming a vapor. Oh yeah, you can also get deposition where a vapor becomes a solid. We see it in the wintertime on frost. And then there's precipitation, which occurs. So humidity is basically a measure of how much moisture the atmosphere can hold. Not how much moisture is in the atmosphere, but how much moisture the atmosphere can hold. We measure humidity and moisture by vapor pressure, mixing ratio, specific humidity, all of these things. So let's discuss some of these a little bit. Vapor pressure. Vapor pressure is the pressure of the gas water vapor. That's all it is. So it doesn't make up a whole lot of our atmosphere. At most, in very, very hot, humid times, it might make up 4% in the lowest kilometer of the atmosphere. But think about it, there's several more kilometers above that. It's not a big amount, but there is a pressure to it. And we know that adding in water vapor adds to the pressure in that sense. It also happens to be lighter than the rest of the air. So, but 4% sometimes in vapor pressure, we can measure vapor pressure. Mixing ratio. It's the mass of water vapor per mass of the remaining dry air. So in other words, if I had a 1 meter by 1 meter by 1 meter cube of air, and I said, oh, I have this much water vapor here. Pull that out of that cube, the remaining dry air. Then compare those. That's the mixing ratio. Specific humidity just adds the mixing ratio, all that moisture back in. So it's going to be slightly different than actual mixing ratio. The absolute humidity is the mass of water vapor per unit volume of humid air, normally expressed as grams of water vapor per cubic meter of air. So air gets saturated. We see it in clouds. So that's when it reaches its maximum relative humidity or humidity. So liquid water literally at that point is evaporating and condensing exactly at the same rate. That is when you reach saturation. So we just talked about vapor pressure, mixing ratio, etc. All of those can have a value of saturation. And changing the air temperature disturbs this. All right. So when we increase the kinetic energy of water molecules, they more easily escape from a surface. So the hotter the air, the hotter the water, the more easier they're going to escape. So that means the hotter the air temperature, the higher more moisture you're going to need, higher values of saturation, vapor pressure, and all to have saturation. And here you can see the calculated values that have been done. And see, really goes up very quickly when you start getting out of wintertime. Wintertime, it's not a lot of moisture in here. It doesn't take a whole lot to saturate the air. But once you start getting into summer, it takes quite a lot of moisture. And we can see the curve here. Also notice, and we're going to get into this a whole lot in the next chapter, but liquid has a higher saturation vapor pressure than ice. It's all because ice is solid and liquid is liquid. Relative humidity is what we hear all the time. All it is vapor pressure over saturation vapor pressure, or mixer ratio over saturation mixing ratio. In other words, it's the percent of water vapor that's in the air compared to the total amount that it can hold. So if you have 100%, that's it. That's all the water vapor that air is going to hold. If you have 50% relative humidity, well, you add another 50%. So take a look at ratio. We know temperature changes how much the air can hold of water vapor, right? So guess what? Relative humidity is going to go up at night because the temperature is going down. Can't hold as much moisture. Then during the day, as the air temperature heats up, it's going to hold more moisture. The relativity is going to actually go down. Actually, in the evening, you'll notice a little spike over here. That little spike occurs because that's when most plants tend to send out their moisture as well. It's an interesting thing to see dew points and the relative humidity actually rise late afternoon. Even though the temperature may not have started to come back down yet, the plants are sending out the maximum amount of moisture at that time. So dew point is just a measure of moisture. Think about it as if you cooled that air where you're at all the way down till it started having little water droplets form on the whatever is cooling the air. Dew would begin to form, or frost. That's the dew point. That is a temperature. You can see how dew points vary. In the wintertime, they're fairly cool. In summertime, they get kind of humid, especially in the southern half along the east coast. So, as the air reaches 100%, you're starting to get clouds. Humidity increases when air is cooled, so we know the air is rising. It's going to begin to form clouds because the air is cooling. If you haven't changed the amount of moisture in the air, eventually you're going to reach a point where it becomes cloudy. We got to talk about stability in the atmosphere, and it relates to moisture. We know that moisture, when it goes from a vapor into a liquid, in other words, when clouds form, heat is released. So that means that air parcel, when it becomes saturated, can't cool as fast as a dry air parcel. So what you're looking at is an air parcel, we'll call it any size you want again, comparing to the surrounding air. The surrounding air might have a temperature dropping at, we'll say, 8 degrees per 1,000 meters, 8 degrees Celsius. Well, if you're rising that air parcel up and it's dry, that air parcel is cooling at 9.8 degrees. Guess what? It's stable. It ain't going to want to go up. It's going to want to come back down. So that air parcel is not going to tend to accelerate upwards. Now, add some moisture in there. All of a sudden, that air parcel is only cooling at about 6 degrees per 1,000 meters. Well, if that air parcel was pushed up 1,000 meters, it's 2 degrees warmer than the surrounding air. That is a significant amount of instability. What does that mean? That air parcel is going to want to accelerate upwards. If you ever look at thunderstorms, that's what's happening in the thunderstorm. The air parcel begins to get cloudy. All of a sudden, it's warmer than the surrounding air. It's going to accelerate upwards. And it's going to keep accelerating until it gets colder than the surrounding air, which may not happen till it reaches the tropopause. Absolute instability, the only way you're ever going to see that I've ever found is if you're right down in the lowest couple centimeters by the surface of the earth. You might actually get that. Conditional instability, on the other hand, is what really drives thunderstorms. It may drive lift that causes rain. So we know that the sun heats the earth, pushes the air up because of convection. We've seen it. That forms these clouds. Oh yeah, hills, mountain ranges form clouds. Fronts. A warm front will be slowly lifting the edge, warmer air aloft. Cold fronts, on the other hand, are very steep. They're going to displace it much faster. Mountains do it. And they eventually reach what they call the lifting condensation level. What's that? It's the level, if I lift a parcel of air up, it has cooled enough that it becomes saturated, and that is where it begins to condense. So that is the bottom of the clouds most times. And we can even see rain shadows would occur if you have a west wind coming into the mountains of the Cascades. On the east side of the mountains, all the moisture's gotten thrown out. because it came down on the other side. Converging winds like sea breezes can lift up. We have around my house right now very little wind, but because of that, there is weak convergence from sea breezes, and we get thunderstorms on them, especially when it's humid like it is right now. So all of that is all about how moisture gets moved and transported. Here are some dew points today. Look at it. Over where I am, dew points are in the mid 70s. Back in Ohio, mid 60s, and even some 50s further back, much drier air back in the Midwest. So you can see this boundary here really separates some very moist air to the east of it. And there's even more moist air. Here's a 79 dew point, which is extremely moist. So I wanted to quickly show you just one sounding. This is Wilmington. There's a lot of dry air. We talk about being very stable. Well, if you pushed an air parcel up, which would probably happen with convection, what's it going to do? It's going to stay dry adiabatic all the way up, because it's literally got to get up to probably close to 20,000 feet before it ever might become saturated. So that air parcel is going to stay dry adiabatic. It means it'll never accelerate upward. It's always going to want to push downward. So this is a very stable sounding. So I hope you got a little bit out of all this, and let me know if you have any questions.